Section 7 of Science and the Modern World by Alfred Whitehead. This LibriVox recording is in the public domain. Chapter 7. Relativity. In the previous lectures of this course we have considered the antecedent conditions which led up to the scientific movement and have traced the progress of thought from the 17th to the 19th century. In the 19th century this history falls into three parts, so far as it is to be grouped around science. These divisions are the contact between the Romantic movement and science, the development of technology and physics in the earlier part of the century, and lastly the theory of evolution combined with the general advance of the biological sciences. The dominating note of the whole period of 3 centuries is that the doctrine of materialism afforded an adequate basis for the concepts of science. It was practically unquestioned. When undulations were wanted, an ether was supplied, in order to perform the duties of an undulatory material. To show the full assumption thus involved, I have sketched in outline an alternative doctrine of an organic theory of nature. In the last lecture it was pointed out that the biological developments, the doctrine of evolution, the doctrine of energy, and the molecular theories were rapidly undermining the adequacy of the orthodox materialism. But until the close of the century no one drew that conclusion. Materialism reigned supreme. The note of the present epoch is that so many complexities have developed regarding materials, space, time, and energy, that the simple security of the old orthodox assumptions has vanished. It is obvious that they will not do as Newton left them, or even as Clerk Maxwell left them. There must be a reorganization. The new situation in the thought of today arises from the fact that scientific theory is outrunning common sense. The settlement as inherited by the 18th century was a triumph of organized common sense. It had got rid of medieval fantasies and of Cartesian vortices. As a result, it gave full rein to its anti-rationalistic tendencies derived from the historical revolt of the Reformation period. It grounded itself upon what every plain man could see with his own eyes, or with a microscope of moderate power. It measured the obvious things to be measured, and it generalized the obvious things to be generalized. For example, it generalized the ordinary notions of weight and massiveness. The 18th century opened with the quiet confidence that at last nonsense had been got rid of. Today we are at the opposite pole of thought. Heaven knows what seeming nonsense may not tomorrow be demonstrated truth. We have recaptured some of the tone of the early 19th century, only on a higher imaginative level. The reason why we are on a higher imaginative level is not because we have finer imagination, but because we have better instruments. In science, the most important thing that has happened during the last 40 years is the advance in instrumental design. This advance is partly due to a few men of genius such as Michelson and the German opticians. It is also due to the progress of technological processes of manufacture, particularly in the region of metallurgy. The designer has now at his disposal a variety of material of differing physical properties. He can thus depend on obtaining the material he desires, and it can be ground to the shapes he desires, within very narrow limits of tolerance. These instruments have put thought onto a new level. A fresh instrument serves the same purpose as foreign travel. It shows things in unusual combinations. The gain is more than a mere addition, it is a transformation. The advance in experimental ingenuity is perhaps also due to the larger proportion of national ability which now flows into scientific pursuits. Anyhow, whatever be the cause, subtle and ingenious experiments have abounded within the last generation. The result is that a great deal of information has been accumulated in regions of nature very far removed from the ordinary experience of mankind. Two famous experiments, one devised by Galileo at the outset of the scientific movement, and the other by Michelson with the aid of his famous interferometer, first carried out in 1881 and repeated in 1887 and 1905, illustrate the assertions I have made. Galileo dropped heavy bodies from the top of the Leaning Tower of Pisa, and demonstrated that bodies of different weights, if released simultaneously, would reach the earth together. So far as experimental skill and delicacy of apparatus were concerned, this experiment could have been made at any time within the preceding 5,000 years. The ideas involved merely concerned weight and speed of travel, ideas which are familiar in ordinary life. The whole set of ideas might have been familiar to the family of King Minos of Crete, as they dropped pebbles into the sea from high battlements rising from the shore. We cannot too carefully realize that science started with the organization of ordinary experiences. It was in this way that it coalesced so readily with the anti-rationalistic bias of the historical revolt. It was not asking for ultimate meanings. It confined itself to investigating the connections regulating the succession of obvious occurrences. Michelsen's experiment could not have been made earlier than it was. It required the general advance in technology and Michelsen's experimental genius. It concerns the determination of the Earth's motion through the ether, and it assumes that light consists of waves of vibration advancing at a fixed rate through the ether in any direction. Also, of course, the Earth is moving through the ether, and Michelsen's apparatus is moving with the Earth. In the centre of the apparatus, a ray of light is divided so that one half ray goes in one direction along the apparatus through a given distance and is reflected back to the centre by a mirror in the apparatus. The other half ray goes the same distance across the apparatus in a direction at right angles to the former ray, and it also is reflected back to the centre. These reunited rays are then reflected onto a screen in the apparatus. If precautions are taken, you will see interference bands, namely bands of blackness where the crests of the waves of one ray have filled up the troughs of the other rays, owing to a minute difference in the lengths of paths of the two half-rays, up to certain parts of the screens. These differences in length will be affected by the motion of the Earth, for it is the lengths of the paths in the ether which count. Thus, since the apparatus is moving with the Earth, the path of one half-ray will be disturbed by the motion in a different manner from the path of the other half-ray. Think of yourself as moving in a railway carriage, first along the train and then across the train, and mark out your paths on the railway track which in this analogy corresponds to the ether. Now the motion of the Earth is very slow compared to that of light. Thus in the analogy you must think of the train almost at a standstill, and of yourself as moving very quickly. In the experiment, this effect of the Earth's motion would affect the positions on the screen of the interference bands. Also, if you turn the apparatus round through a right angle, the effect of the Earth's motion on the two half-rays will be interchanged, and the positions of the interference bands would be shifted. We can calculate the small shift which should result owing to the Earth's motion round the Sun. Also to this effect, we have to add that due to the Sun's motion through the ether. The delicacy of the instrument can be tested, and it can be proved that these effects of shifting are large enough to be observed by it. Now the point is that nothing was observed. There was no shifting as you turned the instrument round. The conclusion is either that the Earth is always stationary in the ether, or that there is something wrong with the fundamental principles on which the interpretation of the experiment relies. It is obvious that, in this experiment, we are very far away from the thoughts and the games of the children of King Minos. The ideas of an ether, of waves in it, of interference, of the motion of the Earth through the ether, and of Michelsen's interferometer are remote from ordinary experience. But, remote as they are simple and obvious compared to the accepted explanation of the nugatory result of the experiment. The ground of the explanation is that the ideas of space and of time employed in science are too simple-minded and must be modified. This conclusion is a direct challenge to common sense, because the earlier science had only refined upon the ordinary notions of ordinary people. Such a radical reorganization of ideas would not have been adopted unless it had also been supported by many other observations which we need not enter upon. Some form of the relativity theory seems to be the simplest way of explaining a large number of facts which otherwise would each require some ad hoc explanation. The theory, therefore, does not merely depend upon the experiments which led to its origination. The central point of the explanation is that every instrument, such as Michelsen's apparatus as used in the experiment, necessarily records the velocity of light as having one and the same definite speed relatively to it. I mean that an interferometer in a comet and an interferometer on the Earth would necessarily bring out the velocity of light relatively to themselves as at the same value. This is an obvious paradox, since the light moves with a definite velocity through the ether. Accordingly, two bodies, the Earth and the comet, moving with unequal velocities through the ether, might be expected to have different velocities relatively to rays of light. For example, consider two cars on a road, moving at 10 and 20 miles an hour respectively, and being passed by another car at 50 miles an hour. The rapid car will pass one of the two cars at the relative velocity of 40 miles per hour, and the other at the rate of 30 miles per hour. The allegation as to light is that, if we substituted a ray of light for the rapid car, the velocity of the light along the roadway would be exactly the same as its velocity relatively to either of the two cars which it overtakes. The velocity of light is immensely large, being about 300,000 kilometers per second. We must have notions as to space and time such that just this velocity has this peculiar character. It follows that all our notions of relative velocity must be recast. But these notions are the immediate outcome of our habitual notions as to space and time. So we come back to the position that there has been something overlooked in the current expositions of what we mean by space and of what we mean by time. Now, our habitual fundamental assumption is that there is a unique meaning to be given to space and a unique meaning to be given to time, so that whatever meaning is given to spatial relations in respect to the instrument on the Earth, the same meaning must be given to them in respect to the instrument on the comet, and the same meaning for an instrument at rest in the ether. In the theory of relativity, this is denied. As far as concerns space, there is no difficulty in agreeing if you think of the obvious facts of relative motion. But even here, the change in meaning has to go further than would be sanctioned by common sense. Also, the same demand is made for time, so that the relative dating of events and the lapses of time between them are to be reckoned as different for the instrument on the Earth, for the instrument in the comet, and for the instrument at rest in the ether. This is a greater strain on our credulity. We need not probe the question further than the conclusion that for the Earth and for the comet spatiality and temporality are each to have different meanings amid different conditions, such as those presented by the Earth and the comet. Accordingly, velocity has different meanings for the two bodies. Thus, the modern scientific assumption is that if anything has the speed of light by reference to any one meaning of space and time, then it has the same speed according to any other meaning of space and time. This is a heavy blow at the classical scientific materialism, which presupposes a definite present instant at which all matter is simultaneously real. In the modern theory there is no such unique present instant. You can find a meaning for the notion of the simultaneous instant throughout all nature, but it will be a different meaning for different notions of temporality. There has been a tendency to give an extreme subjectivist interpretation to this new doctrine. I mean that the relativity of space and time has been construed as though it were dependent on the choice of the observer. It is perfectly legitimate to bring in the observer if he facilitates explanations. But it is the observer's body that we want, and not his mind. Even this body is only useful as an example of a very familiar form of apparatus. On the whole, it is better to concentrate attention on Michelson's interferometer, and to leave Michelson's body and Michelson's mind out of the picture. The question is, why did the interferometer have black bands on its screen, and why did not these bands slightly shift as the instrument turned? The new relativity associates space and time with an intimacy not hitherto contemplated, and presupposes that their separation in concrete fact can be achieved by alternative modes of abstraction, yielding alternative meanings. But each mode of abstraction is directing attention to something which is in nature, and thereby is isolating it for the purpose of contemplation. The fact relevant to experiment is the relevance of the interferometer to just one among the many alternative systems of these spatio-temporal relations which hold between natural entities. What we must now ask of philosophy is to give us an interpretation of the status in nature of space and time, so that the possibility of alternative meanings is preserved. These lectures are not suited for the elaboration of details, but there is no difficulty in pointing out where to look for the origin of the discrimination between space and time. I am presupposing the organic theory of nature, which I have outlined as a basis for a thoroughgoing objectivism. An event is the grasping into unity of a pattern of aspects. The effectiveness of an event beyond itself arises from the aspects of itself which go to form the prehended unities of other events. Except for the systematic aspects of geometrical shape, this effectiveness is trivial if the mirrored pattern attaches merely to the event as one whole. If the pattern endures throughout the successive parts of the event, and also exhibits itself in the whole, so that the event is the life history of the pattern, then in virtue of that enduring pattern, the event gains in external effectiveness. For its own effectiveness is reinforced by the analogous aspects of all its successive parts. The event constitutes a patterned value with a permanence inherent throughout its own parts. And by reason of this inherent endurance, the event is important for the modification of its environment. It is in this endurance of pattern that time differentiates itself from space. The pattern is spatially now, and this temporal determination constitutes its relation to each partial event. For it is reproduced in this temporal succession of these spatial parts of its own life. I mean that this particular rule of temporal order allows the pattern to be reproduced in each temporal slice of its history. So to speak, each enduring object discovers in nature and requires from nature a principle discriminating space from time. Apart from the fact of an enduring pattern, this principle might be there, but it would be latent and trivial. Thus the importance of space as against time, and of time as against space, has developed with the development of enduring organisms. Enduring objects are significant of a differentiation of space from time in respect to the patterns ingredient within events. And conversely, the differentiation of space from time in the patterns ingredient within events expresses the patience of the community of events for enduring objects. There might be the community without objects, but there could not be the enduring objects without the community with its peculiar patience for them. It is very necessary that this point should not be misunderstood. Endurance means that a pattern which is exhibited in the prehension of one event is also exhibited in the prehension of those of its parts which are discriminated by a certain rule. It is not true that any part of the whole event will yield the same pattern as does the whole. For example, consider the total bodily pattern exhibited in the life of a human body during 1 minute. One of the thumbs during the same minute is part of the whole bodily event, but the pattern of this part is the pattern of the thumb, and is not the pattern of the whole body. Thus endurance requires a definite rule for obtaining the parts. In the above example, we know at once what the rule is. You must take the life of the whole body during any portion of that same minute, for example, during a second or a tenth of a second. In other words, the meaning of endurance presupposes a meaning for the lapse of time within the spatio-temporal continuum. The question now arises whether all enduring objects discover the same principle of differentiation of space from time, or even whether at different stages of its own life history one object may not vary in its spatio-temporal discrimination. Up till a few years ago, everyone unhesitatingly assumed that there was only one such principle to be discovered. Accordingly, in dealing with one object, time would have exactly the same meaning in reference to endurance as in dealing with the endurance of another object. It would also follow then that spatial relations would have one unique meaning. But now it seems that the observed effectiveness of objects can only be explained by assuming that objects in a state of motion relatively to each other are utilizing, for their endurance, meanings of space and of time which are not identical from one object to another. Every enduring object is to be conceived as at rest in its own proper space, and in motion throughout any space defined in a way which is not that inherent in its peculiar endurance. If two objects are mutually at rest, they are utilizing the same meanings of space and of time for the purposes of expressing their endurance. If in relative motion, the spaces and times differ. It follows that, if we can conceive a body at one stage of its life history as in motion relatively to itself at another stage, then the body at these two stages is utilizing diverse meanings of space, and correlatively diverse meanings of time. In an organic philosophy of nature, there is nothing to decide between the old hypothesis of the uniqueness of the time discrimination and the new hypothesis of its multiplicity. It is purely a matter for evidence drawn from observations. In an earlier lecture, I said that an event had contemporaries. It is an interesting question whether, on the new hypothesis, such a statement can be made without the qualification of a reference to a definite space-time system. It is possible to do so, in the sense that in some time system or other, the two events are simultaneous. In other time systems, the two contemporary events will not be simultaneous, although they may overlap. Analogously, one event will precede another without qualification, if in every time system this precedence occurs. It is evident that if we start from a given event A, other events in general are divided into two sets, namely those which without qualification are contemporaneous with A, and those which either precede or succeed A. But there will be a set left over, namely those events which bound the two sets. There we have a critical case. You will remember that we have a critical velocity to account for, namely the theoretical velocity of light in vacuo. Also, you will remember that the utilization of different spatio-temporal systems means the relative motion of objects. When we analyze this critical relation of a special set of events to any given event A, we find the explanation of the critical velocity which we require. I am suppressing all details. It is evident that exactness of statement must be introduced by the introduction of points and lines and instants. Also that the origin of geometry requires discussion. For example, the measurement of lengths, the straightness of lines, and the flatness of planes, and perpendicularity. I have endeavoured to carry out these investigations in some earlier books, under the heading of the theory of extensive abstraction, but they are too technical for the present occasion. If there be no one definite meaning to the geometrical relations of distance, it is evident that the law of gravitation needs restatement. For the formula expressing that law is that two particles attract each other in proportion to the product of their masses and the inverse square of their distances. This enunciation tacitly assumes that there is one definite meaning to be ascribed to the instant at which the attraction is considered, and also one definite meaning to be ascribed to distance. But distance is a purely spatial notion, so that in the new doctrine there are an indefinite number of such meanings according to the space-time system which you adopt. If the two particles are relatively at rest, then we might be content with the space-time systems which they are both utilizing. Unfortunately, this suggestion gives no hint as to procedure when they are not mutually at rest. It is therefore necessary to reformulate the law in a way which does not presuppose any particular space-time system. Einstein has done this. Naturally, the result is more complicated. He introduced into mathematical physics certain methods of pure mathematics which render the formulae independent of the particular systems of measurement adopted. The new formula introduces various small effects which are absent in Newton's law. But for the major effects, Newton's law and Einstein's law agree. Now, these extra effects of Einstein's law serve to explain irregularities of the planet Mercury's orbit, which by Newton's law were inexplicable. This is a strong confirmation of the new theory. Curiously enough, there is more than one alternative formula, based on the new theory of multiple space-time systems, having the property of embodying Newton's law, and in addition of explaining the peculiarities of Mercury's motion. The only method of selection between them is to wait for experimental evidence respecting those effects on which the formulae differ. Nature is probably quite indifferent to the aesthetic preferences of mathematicians. It only remains to add that Einstein would probably reject the theory of multiple space-time systems which I have been expounding to you. He would interpret his formula in terms of contortions in space-time, which alter the invariance theory for measure properties, and of the proper times of each historical root. His mode of statement has the greater mathematical simplicity, and only allows of one law of gravitation, excluding the alternatives. But for myself, I cannot reconcile it with the given facts of our experience as to simultaneity and spatial arrangement. There are also other difficulties of a more abstract character. The theory of the relationship between events at which we have now arrived is based first upon the doctrine that the relatednesses of an event are all internal relations, so far as concerns that event, though not necessarily so far as concerns other relata. For example, the eternal objects, thus involved, are externally related to events. This internal relatedness is the reason why an event can be found only just where it is and how it is, that is to say, in just one definite set of relationships. For each relationship enters into the essence of the event, so that apart from that relationship, the event would not be itself. This is what is meant by the very notion of internal relations. It has been usual, indeed universal, to hold that spatio-temporal relationships are external. This doctrine is what is here denied. The conception of internal relatedness involves the analysis of the event into two factors: one the underlying substantial activity of individualization, and the other the complex of aspects, that is to say, the complex of relatednesses as entering into the essence of the given event, which are unified by this individualized activity. In other words, the concept of internal relations requires the concept of substance as the activity synthesizing the relationships into its emergent character. The event is what it is by reason of the unification in itself of a multiplicity of relationships. The general scheme of these mutual relationships is an abstraction which presupposes each event as an independent entity, which it is not, and asks what remnant of these formative relationships is then left in the guise of external relationships. The scheme of relationships as thus impartially expressed becomes the scheme of a complex of events variously related as wholes to parts and as joint parts within some one whole. Even here the internal relationship forces itself on our attention, for the part evidently is constitutive of the whole. Also, an isolated event which has lost its status in any complex of events is equally excluded by the very nature of an event. So the whole is evidently constitutive of the part. Thus the internal character of the relationship really shows through this impartial scheme of abstract external relations. But this exhibition of the actual universe as extensive and divisible has left out the distinction between space and time. It has in fact left out the process of realization, which is the adjustment of the synthetic activities by virtue of which the various events become their realized selves. This adjustment is thus the adjustment of the underlying active substances, whereby these substances exhibit themselves as the individualizations or modes of Spinoza's one substance. This adjustment is what introduces temporal process. Thus, in some sense, time, in its character of the adjustment of the process of synthetic realization, extends beyond the spatio-temporal continuum of nature. There is no necessity that temporal process, in this sense, should be constituted by one single series of linear succession. Accordingly, in order to satisfy the present demands of scientific hypothesis, we introduce the metaphysical hypothesis that this is not the case. We do assume, basing ourselves upon direct observation, however, the temporal process of realization can be analyzed into a group of linear serial processes. Each of these linear series is a space-time system. In support of this assumption of definite serial processes, we appeal 1. To the immediate presentation through the senses of an extended universe beyond ourselves and simultaneous with ourselves. 2. To the intellectual apprehension of a meaning to the question which asks what is now immediately happening in regions beyond the cognizance of our senses. 3. To the analysis of what is involved in the endurance of emergent objects. This endurance of objects involves the display of a pattern as now realized. This display is the display of a pattern as inherent in an event, but also as exhibiting a temporal slice of nature as lending aspects to eternal objects, or equally of eternal objects as lending aspects to events. The pattern is spatialized in a whole duration for the benefit of the event into whose essence the pattern enters. The event is part of the duration, that is part of what is exhibited in the aspects inherent in itself, and conversely the duration is the whole of nature simultaneous with the event, in that sense of simultaneity. Thus an event in realizing itself displays a pattern, and this pattern requires a definite duration determined by a definite meaning of simultaneity. Each such meaning of simultaneity relates the pattern as thus displayed to one definite space-time system. The actuality of the space-time systems is constituted by the realization of pattern, but it is inherent in the general scheme of events as constituting its patience for the temporal process of realization. Notice that the pattern requires a duration involving a definite lapse of time, and not merely an instantaneous moment. Such a moment is more abstract, in that it merely denotes a certain relation of contiguity between the concrete events. Thus a duration is spatialized, and by spatialized is meant that the duration is the field for the realized pattern constituting the character of the event. A duration, as the field of the pattern realized in the actualization of one of its contained events, is an epoch, that is, an arrest. Endurance is the repetition of the pattern in successive events. Thus endurance requires a succession of durations, each exhibiting the pattern. In this account, time has been separated from extension and from the divisibility which arises from the character of spatio-temporal extension. Accordingly, we must not proceed to conceive time as another form of extensiveness. Time is sheer succession of epochal durations. But the entities which succeed each other in this account are durations. The duration is that which is required for the realization of a pattern in the given event. Thus the divisibility and extensiveness is within the given duration. The epochal duration is not realized via its successive divisible parts, but is given with its parts. In this way, the objection which Zeno might make to the joint validity of two passages from Kant's Critique of Pure Reason is met by abandoning the earlier of the two passages. I refer to passages from the section of the Axioms of Intuition, the earlier from the subsection on extensive quantity, and the latter from the subsection on intensive quantity, where considerations respecting quantity in general, extensive and intensive, are summed up. The earlier passage runs thus: I call an extensive quantity that in which the representation of the whole is rendered possible by the representation of its parts, and therefore necessarily preceded by it. I cannot represent to myself any line, however small it may be, without drawing it in thought, that is, without producing all its parts one after the other, starting from a given point, and thus, first of all, drawing its intuition. The same applies to every, even the smallest portion of time. I can only think in it the successive progress from one moment to another, thus producing in the end, by all the portions of time, and their addition, a definite quantity of time. The second passage runs thus: this peculiar property of quantities, that no part of them is the smallest possible part, no part indivisible, is called continuity. Time and space are quanta continua, because there is no part of them that is not enclosed between limits, points and moments, no part that is not itself again a space or a time. Space consists of spaces only, time of times. Points and moments are only limits, mere places of limitation, and as places presupposing always those intuitions which they are meant to limit or to determine. Mere places or parts that might be given before space or time could never be compounded into space or time. I am in complete agreement with the second extract if time and space is the extensive continuum, but it is inconsistent with its predecessor. For Zeno would object that a vicious infinite regress is involved. Every part of time involves some smaller part of itself, and so on. Also this series regresses backwards ultimately to nothing, since the initial moment is without duration and merely marks the relation of contiguity to an earlier time. Thus time is impossible, if the two extracts are both adhered to. I accept the later and reject the earlier passage. Realization is the becoming of time in the field of extension. Extension is the complex of events, qua their potentialities. In realization, the potentiality becomes actuality. But the potential pattern requires a duration, and the duration must be exhibited as an epochal whole, by the realization of the pattern. Thus time is the succession of elements in themselves divisible and contiguous. A duration, in becoming temporal, thereby incurs realization in respect to some enduring object. Temporalization is realization. Temporalization is not another continuous process. It is an atomic succession. Thus time is atomic, that is epochal, though what is temporalized is divisible. This doctrine follows from the doctrine of events and of the nature of enduring objects. In the next chapter we must consider its relevance to the quantum theory of recent science. It is to be noted that this doctrine of the epochal character of time does not depend on the modern doctrine of relativity, and holds equally, and indeed more simply, if this doctrine be abandoned. It does depend on the analysis of the intrinsic character of an event, considered as the most concrete finite entity. In reviewing this argument, note first that the second quotation from Kant, on which it is based, does not depend on any peculiar Kantian doctrine. The latter of the two is in agreement with Plato as against Aristotle. In the second place, the argument assumes that Zeno understated his argument. He should have urged it against the current notion of time in itself, and not against motion, which involves relations between time and space. For what becomes has duration, but no duration can become until a smaller duration, part of the former, has antecedently come into being, Kant's earlier statement. The same argument applies to this smaller duration, and so on. Also, the infinite regress of these durations converges to nothing, and even on the Aristotelian view there is no first moment. Accordingly, time would be an irrational notion. Thirdly, in the epochal theory, Zeno's difficulty is met by conceiving temporalization as the realization of a complete organism. This organism is an event holding in its essence its spatio-temporal relationships, both within itself and beyond itself, throughout the spatio-temporal continuum. End of section 7.